Hello, everyone. Welcome to pre-lecture 6. This is going to be for our lecture on Thursday. Okay, so we're hopefully finishing up chapter 11 by the end of class, and the end of chapter 11 talks about something called colligative properties of solutions. And so these are properties that are affected by the concentration of our solute in our solution. And so before we get to that point, I also want to take a moment to review, or maybe for some of you, to learn some different measures of concentration. And so molarity is the one we're probably most used to working in. I know we've worked in it in class before. So molarity is equal to the moles of our solute over the liters of our solution, right? This is a great measurement for a number of reasons. However, one potential issue with it is that it uses the volume of solution, and that is something that is temperature dependent. And so if we're doing something that varies over a range of temperatures, that would mean that our molarity is also going to change over that range of temperatures. And so we're going to have some different units of measurement in order to kind of help us better classify things that might be temperature dependent, or just ways we can report different measures of concentration that are useful. Okay, first of those is a mole fraction. So this is designated by uppercase X. This is technically the Greek symbol chi. So chi sub A, and it is the moles of A, which can be our solvent or our solute, just one of our components, over the total moles of all components. And so if you have two things, it would be the sum of those two things, their moles. If you had three things, it would be the sum of those three things and all their moles. Okay, that is mole fraction. We also have molality. This is lowercase m as compared to uppercase m for molarity. And this is defined as the moles of our solute divided by the kilograms of our solvent. And so molality is kind of the weird one of all our units of concentration, in that with molality, the denominator here is just referring to our solvent rather than our solution or all of our components. Okay, so that's something to keep in mind. We also have different measures of essentially parts. And so we have mass percent, which is probably something you've seen before, essentially the mass of the solute over the mass of the solution times 100. Percent just means multiplied by 100. Parts per million then is the same initial thing, where we have the mass of our solute over the mass of our solution, but instead of multiplying it by 100 to get to mass percent, we get parts per million, which is times 10 to the 6th, which is 1 million there. Okay, and for parts per billion, again, same thing, but times 10 to the 9th. Okay, so moving on to colligative properties, when we have a non-volatile substance, solute, such as salt or sugar, and we dissolve it in a liquid, it can lower that liquid's vapor pressure. This is called vapor pressure depression. There's a meme for you. And so this phenomenon can be rationalized in a couple of ways. Essentially, what we want to think of, though, is that when we dissolve a non-volatile solute in our solution, essentially that solute's going to take some of the spaces at the top of our solution there, and that's going to prevent the vaporization of our liquid to our gas. And so what that means is that by blocking those spots, by having those solute molecules take up some of the top spots on our solution, we're going to lower the vapor pressure of our solution because it is not as easily able to vaporize. Okay. Our rate of condensation is not going to be affected by the presence of that solute. And so again, our net result is that our vapor pressure is going to be lowered. And that is because we have solute molecules that are taking up spots on the top of our solution and preventing the vaporization of, in this case, water, which is our solvent. Okay. We can measure this using something that looks similar to Henry's law, but this is called Raoult's law. And so in Raoult's law, we can take the partial pressure that is exerted by any component of an ideal solution and figure out its vapor pressure by using this relationship here. So P sub A is the partial pressure of any component. That's again going to be a vapor pressure. and then chi x, this is our mole fraction measurement, and then PA star is just that single component, okay? And so one thing to keep in mind that's very important for our solubility, or not our solubility rather, but our colligative properties, is that they are affected by how many particles total dissolve. And so, for example, if we have sodium chloride, when it dissolves, we produce 2 moles of solute, meaning that it would have double the effect compared to something like sugar, that's a non-electrolyte, something that doesn't dissolve. And that means that we would get essentially a greater vapor pressure depression with sodium chloride compared to like sugar. Okay. So one of the places this is important in society is the purification of crude oil. So if we have crude oil, essentially we can heat it in these large towers. If you've ever driven by an oil refinery, you'll see a lot of these. Essentially at these different levels, these gases have different vapor pressures, and they are sorted out by their vapor pressures essentially. Okay, so the smaller the molecule, because they're all hydrocarbons, the smaller the molecule, the higher it will go, and the larger the molecule, the lower it will go. Okay. So similar to vapor pressure depression, we also have boiling point elevation. And so if we lower vapor pressure, that should mean we have a higher boiling point as well. And so we can calculate that change in boiling point using this equation here, where we have the change in temperature of our boiling point is going to be Kb multiplied by Kb, which is the boiling point elevation constant. If you ever need it, that will be given to you. Again, this is kind of similar to our Henry's law. And then m is molality. So again, anytime you see lowercase m in this unit, we're talking about the molal concentration of the solute species. Okay. This is another thing that is a colligative property. So it's going to be affected by the total number of solute particles. Okay, so it doesn't matter what your solvent is, not the mass or the size of the chemicals, but just the number of solute particles. So something to keep in mind. Right, we also have freezing point depression. And so this is another thing that is going to be the lowering of a solution's freezing point compared to it as a pure liquid. And so this essentially happens when a solute prevents or at least makes more difficult the formation of a solid phase. And so we can measure that using this equation where we have, again, essentially these same things. I have a typo here. This shouldn't be Kb, this should be Kf. It's a different constant for the freezing point depression that, again, will be given to you. And for this, we use our molality, right? Okay. So if we think about this in terms of a phase diagram, we can see our boiling point elevation and our freezing point depression by changes in our phase diagram shown here in the dotted lines. Okay, so I'll let you take a look at that. If you have any questions, please let me know. I'll be happy to help. But that is it for our pre-lecture today. We'll see you in class.